There is a laboratory experiment that completely violates common sense. It breaks our understanding of reality so completely that physicists openly joke about it. Jim Al-Khalili from the University of Surrey has a standing challenge. If you can explain this phenomenon using standard logic, he claims there is a Nobel Prize waiting for you. For over a century, no one has claimed it. The mystery begins in 1801. Thomas Young fired light through a screen with two parallel slits in it. Instead of getting two bright bands on the wall behind the screen, he got a series of alternating bright and dark stripes. This is an interference pattern. It happens when two waves overlap and cancel each other out. This proved light moves as a wave. But in the 20th century, physicists repeated the experiment using individual electrons. These are solid particles of matter. They fired them one at a time, expecting each one to pass through a single slit and hit a single spot. Instead, as the individual impacts built up on the screen, that exact same wavy interference pattern emerged. Think about what that requires. An interference pattern needs two waves overlapping, but there was only one electron at a time. To create that pattern, a single particle must have gone through both slits simultaneously, interfering with itself. That makes no sense under the rules of classical physics. So scientists decided to watch. They placed a detector right at the slits to record exactly which path the individual electron was taking. The moment they turned the detector on, the interference pattern vanished. The electrons stopped acting like waves. They hit the back wall in two distinct clumps, behaving exactly like solid particles making a choice. How does the mere extraction of information force reality to choose a shape? The detector didn't physically bump the particle, it only watched. In July 2025, physicists at MIT confirmed this with stunning precision. Using atoms as slits, they proved mathematically that the more exact information you gather about a particle's path, the less it behaves like a wave. Acquiring information and maintaining wave behavior are mutually exclusive. The universe, it seems, demands a definitive choice only when someone is looking. As baffling as that is, the physicist John Archibald Wheeler realized things could get stranger. He proposed an experiment where you wait until after the particle passes through the slits, and then decide whether to observe which path it took. In the delayed choice experiment, measuring the particle after the fact still determines whether it forms a wave or particle pattern. With the quantum eraser, if you permanently delete that path data before looking, wave behavior returns, even though the physical journey is already complete. If a measurement made right now can dictate whether a particle acted like a wave or a solid object a microsecond ago, what does that mean for the arrow of time? It suggests the past is not a fixed physical certainty. The history of that particle remains undecided until the future extracts information from it. The rules of reality break down across space too. Take quantum entanglement. This is a phenomenon where two particles become linked. If you measure the state of one, the other instantly snaps into a corresponding state. Albert Einstein famously called this spooky action at a distance. To him, for one particle to instantly dictate the state of another, a signal must travel between them faster than light. And according to his theory of relativity, that is impossible. So how do two separated particles communicate their states instantly without sending a physical signal? They don't communicate. In 2022, Elaine Aspect and a team of physicists won the Nobel Prize for tests proving Bell's theorem. They generated hard, experimental evidence showing that entanglement is real, and no hidden signals are passing between the particles. Extracting information from a particle here instantly forces reality to render over there. The universe operates non-locally. Distance, at the quantum level, simply does not dictate the rules. Erwin Schrödinger tried to highlight how absurd this all is with his famous thought experiment. If you place a cat in a box with a radioactive trigger, quantum mechanics suggests the animal exists in a superposition, both alive and dead, until you open the box and force an outcome. Physicists still fiercely debate what this actually means. Niels Bohr argued that the mathematics simply predict outcomes, and we shouldn't ask what the particle is doing when we aren't looking. Others support the many worlds theory, which asserts that every possible outcome physically occurs, constantly splitting the universe into infinite branching realities. This tension sparked some of the most intense debates in modern science. Einstein insisted that a particle must have a definite path, even when unobserved, while Bohr maintained that the observation itself brings the property into being. We have equations that predict these behaviors with flawless accuracy. But does it matter that we have absolutely no idea what those equations describe about our actual reality? For 100 years, the greatest minds in history have gathered to debate this exact question, and yet no single interpretation of objective reality has ever won out. Every atom, every chemical bond, and every firing neuron in your body operates entirely on these unresolved quantum rules. We have built the modern technological world on top of this math. Our computers, lasers, and MRI machines all depend on it. Yet we still don't know if the physical stuff making up those machines actually has a definite form before we look at it. The most tested theory in science says that particles have no path until measured. Does that lack of objective reality disturb you? Or does it make the universe feel a little more honest?